So in this class, we will discuss a problem on torsion of multiply connected thin wall section. So this is the section given. So you can see that there are two compartments here, rectangle compartments. The dimensions being center to center line dimensions being 25 mm, here it is 40 mm, and the width is 50 mm for both. And thickness is different here. I will take thickness of this one as T1, which is 2 mm. This is T2, which is 1.5 mm, and it is T3, that is 3 mm. Now, the question here is, he has given the torque carried by this total section 300 Newton meter. If you convert that into Newton millimeter, it is 300 into 10 power 3. G value has given 30 GPa, that is 30 into 10 power 3 MPa. Now he has asked what is the twist, angle of twist per unit length or per millimeter of this section, and what is the maximum shear stress that is going to develop in this section. Of course, he has given the torque value here. One thing we have to keep it in mind that there are two cells here. These two are called as cells. This is one cell, this is another cell. So areas of these two cells, I can take them as A1 and A2. So area of A1 is the center line bounded area, that is 25 by 50, which comes out to be 1000 mm square. Area of this portion or segment is 40 into 50, that is 2000 mm square. Now the torque, whatever he has given, so that is the torque, total torque. So total torque means you can just split the total torque into two torques. So one taken by this cell, another one taken by this cell, T1 and T2. So T is equal to T1 plus T2 now. So we know that T1 is 2A1Q1 and T2 is 2A2Q2 because T is 2AQ. We know that relationship. Now here there are two shear flows here. Q1 is the shear flow in this first cell, whereas Q2 is the shear flow in the second cell. So here what happens, A1 is this value 1000 and A2 is 2000. If you substitute in this equation, so T is known here, total torque is given. So if you substitute that 300 into 10 cube, that is Newton millimeter, that is the value of T, is equal to 2 into A1. This is Q1. Q1 actually we know that Q1 is tau 1 into T1. So tau into T is Q. So Q is the shear flow, tau is the shear stress, T is the thickness of the tube. Now here tau 1 is unknown, T1 is 2 mm, so it is 2 tau 1, and Q2 it is tau 2 into T2, so which is T2 is 1.5, so 1.5 into tau 2 I can substitute. So if you substitute in this equation, so this is 300 into 10 power 3, 2 into A1 is 1000, Q1 becomes 2 tau 1 plus 2 into A2 is 2000 into Q2 is 1.5 tau 2. If you simplify this, you get an equation in terms of tau 1 and tau 2. So 5 tau 1 plus 6 tau 2 is equal to 300. So here please note that tau 1, tau 2, they are the unknown things. Now another equation we can develop by taking, we can also call it as continuity equation. So if you observe this here, so if you take this flow in this middle web portion, this is called as the web portion, middle web portion. If you take that as Q3, so what you can say here is, suppose you take this point A, so you will be having a Q1 in this direction and Q2 will be away from A like this and Q3 will be like this. Similarly, tau 1, tau 2, tau 3. So here what happens, so this tau 1, whatever Q1, whatever is the shear flow in this portion, so that will be split into two Qs, Q2 and Q3. That means you can write it as Q1 is equal to, so this is split into two parts, so Q2 plus Q3. So you can see here, this Q1 is diverted in two directions, so Q2 plus Q3. Or in other words, Q1 is tau 1 T1, Q2 is tau 2 T2, Q3 is tau 3 T3. So you can here once again T1 is 2 mm, so it becomes 2 tau 1 is equal to T2 is 1.5 mm, so 1.5 tau 2 plus T3 is 3 mm, 3 tau 3. So this is the second equation. So first equation in terms of tau 1 and tau 2, second equation in terms of tau 1 tau 2, tau 3. In all the three tau values, we will get the second equation. Now we cannot solve because there are three unknowns, tau 1, tau 2, tau 3, and there are only two equations. So that is why we are going to use one more very important equation, which is called as compatibility equation or compatibility condition. So this compatibility condition, in case of torsion, it will be in terms of angle of twist. So angle of twist remains same for both the cells. So that means whatever theta 1 is there for this, then theta 2 also will be there the same. So theta 1 is equal to theta 2. That is called as the compatibility equation in the case of torsion. So that means another expression we can always derive this expression. Anyway, I am not going to in detail about that. But you remember this expression. So this 2 g theta, whatever is there, this can be expressed. This can be expressed in terms of shear stress, length of flow, and area. Shear stress, length of flow, and area. Now, how to write that? So for the first cell, so this is for the first cell. This is for the second cell. So what we do is, whatever 2g theta is there for the first cell will be the same as 2g theta for the second cell. So what happens here is, in the first cell, if you consider the first cell, if you see this diagram, this tau 1 and tau 3 we have to consider in the first cell. So all of you please observe here. So this tau 1 is in this direction, tau 3 also is in the same direction. So this is tau 3. So tau 1 and tau 3 they are in the same direction, and tau 1 is multiplied by S1. What is this S1? S1 is the flow over which tau 1 takes place. So tau 1, this is also tau 1, this is also tau 1. So tau 1 will be there here, here, and here. This is also tau 1. So tau 1 will be there in this, except this middle red portion. So this 25 mm, 50 mm, 25 mm. So that is your S1. So that 50 plus 25 plus 25. Similarly, S2 is the length of flow of tau 2. Length of flow of tau 2. So this is tau 2, this is also tau 2, and this is also tau 2. Now the length of flow will be here. This is 40, this is 50, this is 40. So total is 130. So S2 will be corresponding to tau 2, and S3 will be corresponding to tau 3. So this tau 3 will be there only here in the middle left portion, whose length is 50 mm. So therefore S3 is 50 mm. So S1 is 100 mm, S2 is 130 mm, S3 is 50 mm. And A1 here as already told, it is now here A1 is 25. Sorry, here it is. I think this is 25. This is 1250. So here also this will be 1250. Okay, no mistake there. So A1 is 1250 mm square, A2 is 40 into 50, that is 2000 mm square. So now if you substitute these things here in this equation, equation 3 I have taken here, substituting equation 3, so tau 1 into S1 is 100 plus tau 3 into S3 is 50 divided by A1 is 1250. This will be equal to tau 2 into S2. Now here minus sign will come here. Why this is plus sign here is, so tau 1 and tau 3 they are in the same direction. So tau 1 is like this, tau 3 is like this. They are running in the same direction. That is why it is plus here. Whereas here it is negative because tau 2 runs like this and tau 3 will not run like this. Tau 3 is going here. So they are running in the opposite directions. That is why minus we have to take. This step is very important. Here plus is there, here minus is there. So these two should be equal. So if you substitute the RHS, tau 2 into S2 is 130 minus tau 3 into S3 is 50 divided by A2 is 2000. Now if you simplify this cross multiplication, if you simplify, you will get another equation in terms of all the three, tau 1, tau 2, tau 3. So this is what the simplified equation you are going to get. You can call this as equation 4. So that means these two equations already we have. One from the torsion expression, another from the shear flow expression. So two equations already you have. This is the third equation from the compatibility condition. We got this third equation. So now you have three equations and you have three unknowns. So you can solve. So tau 1, tau 2, tau 3, three unknowns are there. So you can solve those three. Equation 1, equation 2 and equation 4. If you solve, so these are the values you are going to get in MPA. So tau 1, tau 2, tau 3, they are expressed in MPa. Suppose if any of these values comes out to be negative, understand it, comes out to be negative, the flow is in the other direction. Suppose if you take tau 2 as negative, that means like this, then the tau 2 will be in the opposite direction. That's all. Answer is correct. So only numerical, if they are positive, then it assumed direction of shear flow is correct. If you get negative value, it is in the opposite direction. That's all the interpretation. Now here, once you get these three values, now out of these three, this is your tau max. You can see the highest value is tau 2, and that is your tau max value. Now the angle of twist you can once again get from this equation 3 itself. You know that 2g theta is equal to, either you can take this or this. So if you want theta, so theta will be, now I am taking this, tau 1 s1 plus tau 3 s3 divided by a1 is there. This 2g, it comes to the denominator, so into 2g will come here. Now you know all the values, tau 1 value you know, tau 3 value you know, s1, s3, all those things you know. A1 is 1250 into 2 into g is 30 into 10 power 3. If you simplify that, you get the value of theta in radian per mm. So it's a very, very small value, 3.23 into 10 power minus 5 radian per millimeter. So if you know the length of that section or the cube, thin wall cube, whatever it is, so then you can multiply this value by the length to get the total angle of twist. So this angle of twist is expressed as radian per millimeter. So this is how we have to tackle a problem of multiply connected thin walled cells. There are two cells here. So similarly they can give 3 cells or 4 cells. So what that means, initially we have to assume some direction of shear flow and tau in terms of tau and q, all those things. So you can always use the given data for developing the equations. Since here t is given here, we have to use the equation t is equal to t1 plus t2 and we have to proceed. And second is the shear flow equation based on the directions. Based on the directions, you can write that in terms of q1, q2, q3. So you will get one more equation. Then the third equation is the compatibility equation. In terms of all the three, you are going to get. Then by solving all these three equations, you can get the values of tau 1, tau 2, tau 3. And then if they ask you to find the angle of twist, you have to use the compatibility equation once again to get the angle of twist. So in the next class, I will be solving one more problem of this type.